Hello and welcome to the AICE Chemistry Lecture Series. Today we're going to look at section 7.2, which is going to look at oxidation numbers. Oxidation numbers are an integral part of doing redox reactions, so we need to make sure that we properly learn how to use them and how to assign them to different elements. So let's get started. Oxidation numbers, otherwise known as oxidation states, are essentially a way to keep track of the reduction and oxidation sides of a redox reaction, especially for non-ionic species, because for ions, it's very simple to track whether they're losing or gaining electrons because they will have a charge. However, when we have something a little more complex, like a compound or a polyatomic ion, it's a lot harder to see where those electrons are going. Because remember, a redox reaction, reduction and oxidation, is all about the transfer of electrons. Reduction is the gain of electrons, oxidation is the loss of electrons. So in order to properly talk about these reactions, we need to make sure we can follow where these electrons are going. Oxidation numbers can be both positive or negative whenever we look at them. The more positive the oxidation number of an element is, we say the more oxidized that element is. And this is a very important concept because two parts here. One is that oxidation numbers are assigned not to a compound, but to individual elements in that compound. For example, here in sodium chloride, the sodium has an oxidation number of +1, the chlorine oxidation number of -1. In KMnO4, potassium dichromate, potassium has an oxidation number of +1, manganese an oxidation number of +7, and each oxygen out of the four has an oxidation number of -2. So oxidation numbers are assigned per element, not per compound. The other part of this is that the oxidation numbers are named oxidation numbers because the higher the number, the more oxidized an element is. Now, what exactly does that mean? Well, oxidation numbers are something that we have created to keep track of oxidation. Something that is more oxidized essentially means that it is more electron deficient. It is something that will have lost electrons. Now, that concept is not particularly too important, but the comparison of oxidation numbers is. Something with a higher oxidation number, like the positive one here in sodium chloride, versus the negative one in chlorine, means that the sodium was oxidized to get to this point, whereas the chlorine, or chloride in this case, because it's a negative number, was more reduced. So the more negative an oxidation number is, also the more reduced the element is, the more electrons it has gained, whereas the more positive it is, the more electrons it has lost. The same element can have different oxidation numbers in different compounds, and that's very important to understand. For example, oxygen, when it's neutral or in ozone, has an oxidation number of 0. But oxygen in the potassium permanganate here has an oxidation number of -2, whereas oxygen in OF2 has an oxidation number of +2. So that's 3 different oxidation numbers for the same element. O2 has an oxidation number of 0 for the oxygen, KMnO4 has an oxidation number of -2 for the oxygen, and OF2 has an oxidation number of +2. So keep that in mind as we go through this, because some elements will have only one oxidation number, whereas others can have multiple. So now that we have a basic idea of what oxidation numbers or oxidation states are, let's look at how to apply them. Oxidation numbers are applied to different elements by following certain rules. So what we're going to do is we're going to go over these rules in this video in section 7.2, and then in section 7.3 we're going to look at how to apply those rules to different compounds. So oxidation numbers can be assigned to different elements by following a simple set of rules. Those rules are that the oxidation number of any uncombined element is 0. That's the number one rule, and these rules are a bit of in order of importance, meaning that if we are up here, this rule takes priority over all others. So if any element is uncombined, an uncombined element means an element either that is monatomic or diatomic but an element by itself. So here we can see, if we go back, how C, O2, O3, H2, and Cl2 all have an oxidation number of 0. The reason for that is that these elements are uncombined. Even though oxygen, hydrogen, and chlorine are diatomic, and ozone is triatomic in O3, because it's an element by itself, not in a compound or not as an ion, it's a neutral element by itself or paired up with itself, then its oxidation number will be 0. Oh, wrong way. That's the first rule. And that's going to supersede any other rule. So if you see anything else here that contradicts rule number 1 will always take precedence if it's applicable. Number 2, in compounds, many atoms or ions are fixed, meaning that if they're not in an element by themselves, an uncombined element, there are certain elements that have a fixed oxidation number. Group 1 elements like sodium, for example here, or potassium here, are always going to have an oxidation number of +1. Similarly, group 2 elements are always going to have an oxidation number of +2. So this is always going to be the case. Let me bring up our periodic table here. So if we look at our periodic table, that means that our elements, some of them, will have a fixed oxidation number. So, for example, elements in our first column are always going to have a +1 oxidation number. So anything in group column 1, lithium, sodium, potassium, rubidium, cesium, francium, are always going to have a +1 oxidation number. Likewise, we said that group 2 elements are going to have a +2 oxidation number. So anything here in group 2 is going to have a +2 oxidation number. So beryllium, magnesium, calcium, strontium, barium, or radon, if they're in a compound, are always going to have a +2 oxidation number. So that's always going to be the case. There are no exceptions to that rule. Another element that has a fixed oxidation number is fluorine. Fluorine, F over here, is always going to have a -1 oxidation number. This is not the whole group. The whole group can have variable oxidation numbers. Fluorine specifically will always have a -1 oxidation number. Hydrogen has a variable oxidation number, but it is variable with specific rules, meaning that hydrogen will always be +1, except when hydrogen is found in a metal hydride. Metal hydrides being any metal combined with hydrogen. In that case, hydrogen will have a -1 oxidation number. So we go back here, hydrogen is always going to be +1, except, and that's an acronym here, except in metal hydrides, where it's going to be a -1 oxidation number. So if hydrogen is, say, in water, for example, H2O, it will be +1. But if it's in a metal hydride, like sodium hydride here, NaH, or when it's paired up with any metal, essentially, it's going to be a -1 oxidation number. Similarly is oxygen. Oxygen is another one of those elements that has variable oxidation numbers, but with specific rules. In most cases, oxygen will have an oxidation number of -2. And this is true 95% of the time. Unlike metal hydrides, the exceptions for oxygen are a lot less common. Oxygen will be usually in -2 oxidation number, except in peroxides, and really the only peroxide that we really see in AS chemistry is hydrogen peroxide, H2O2. In hydrogen peroxide and other peroxides, oxygen has an oxidation number of -1 instead of -2. And then the only time that oxygen will be positive is in F2O, when combined with fluorine, oxygen will have an oxidation number of +2. So essentially, oxygen is very complex. Most of the time, 95% of the time, oxygen will have a -2 oxidation number, but it will be -1 in peroxides, so which is usually just H2O2 for us, and will be negative or +2, sorry, only in F2O. And I can't really put lowercase letters here, but only in F2O will oxygen be positive. So that is our rule for oxygen. -2, 95% of the time. -1 in peroxide, like hydrogen peroxide, and +2 in F2O. And it's particularly that particular combination of oxygen and fluorine. These are the ones that have fixed oxidation numbers or some kind of variability, but with very strict rules. After that, we need to use rules 4 through 6 for all the other elements. And rules for 3 through 6 are as following. The oxidation number of any monoatomic ion is the same as its charge. And that's very straightforward and very logical, considering that the charge of an ion is going to come from how it gains or loses electrons. So very straightforward is that for something aluminum, Al3+, the aluminum ion, its oxidation number is simply +3. So notice how here we have the charge, which is number then sign, but with oxidation numbers we have sign then number. This is a common way of writing the oxidation numbers, is usually to put the sign and then the number, which is why, generally speaking, for charges we put the number and then the sign, even though they are going to be the same. Now, this is not only true of ions in the ionic state like we have here, but also true of ionic compounds. For example, here we have sodium chloride, where the sodium ion has a +1 oxidation number, whereas the chloride has a -1. The reason why is that this sodium chloride is an ionic compound. And like we know, ionic compounds are made out of ions. So here, sodium is really Na+, the ion of sodium, whereas Cl is Cl minus the ion of chlorine. So we have the same rule here where this charge directly translates to the oxidation number. The +1 charge on the sodium is a +1 oxidation number on the sodium. The -1 on the chloride ion is the -1 oxidation number for the chlorine. And that's because sodium chloride is an ionic compound. And ionic compounds are made out of ions. And because of that, these are the oxidation numbers for those elements. So that's something that we can derive from the third rule. It's not just ions by themselves, like if we have sodium Na+, we will know it's +1 oxidation number, but the compound NaCl, the compound of sodium chloride, is going to have the oxidation numbers match the ion charges for that ionic compound. Next is number 4. The sum of the oxidation numbers in a compound is always going to be equal to 0. Now, this is a very important rule along with rule number 5. Rule number 5 says something similar. The sum of the oxidation numbers in an ion, a polyatomic ion, is going to be equal to the charge of the ion. So we are going to apply rules 4 and 5 along with any rule that we can apply from number 2 and 3 in order to figure out the oxidation numbers for any element that we cannot figure out from these rules. And we're going to see how to use these two rules in the video for 7.3. But in essence, all we're doing is just adding up oxidation numbers, figuring out what the charge of the ion is, or if it's a compound, neutral, so 0, and then making sure that all of those elements add up to that charge or that zero for compounds. And again, we'll see how to in the next video. The last rule is that the more electronegative the element is, the more negative the oxidation number is going to be. Meaning that if you have elements that you're putting together, the more electronegative element is always going to get a negative oxidation number with it. So that's why if we go back to the rule for oxygen, oxygen is always negative. -2 for oxygen most times, -1 for peroxides, because element is the second most electronegative element. So it makes sense for its oxidation number to be negative. The only time oxygen is ever positive is when it's in F2O. And that's because fluorine is the most electronegative element. So by fluorine being the most electronegative element, it is the only time where oxygen, the second most electronegative element, will have a positive oxidation number. Because out of the two, the more electronegative one, fluorine, will have to be negative. So this last rule is not so much a rule that we're going to use, but a rule that explains why the negative oxidation numbers are given to certain elements, like the fluorine in the case of F2O. All right. So those are the oxidation number rules. So the ones that we know for sure, remember, are that anything by itself is going to have an oxidation number of 0, and that's always going to be the main case. So anything like O2, O3, C, H2, they're always going to be 0 oxidation numbers because they're elements by themselves. After that, we know for sure that any group 1 element will have a +1 oxidation number. Any group 2 element will have a +2 oxidation number. Hydrogen will always be +1, except in a metal hydride when it's -1. And that metal hydride, remember, is any metal with hydrogen. And then fluorine will always be -1. Oxygen will most of the time be -2, with 2 exceptions. With peroxides, like hydrogen peroxide, it will be -1. With F2O, it will be +2. Other than that, we're going to have to use rules 3, 4, and 5 in order to figure out any other element. So if element's an ion or in an ionic compound, its charge, its oxidation number. And otherwise, we'll have to add up the oxidation numbers to get 0 for a compound or the ion's charge for a polyatomic ion. So that's it for this section. We will continue this conversation in the video for 7.3 when we're going to look at how to apply the oxidation number rules.